Somewhere deep inside a cryogenic chamber, cooled to temperatures colder than outer space, a signal was sent into the quantum realm. Not a radio wave, not a laser pulse. Something stranger than either of those, a precisely engineered whisper directed into the fabric of reality itself, into the invisible machinery that underlies everything you've ever touched, seen, or thought. The scientists running the experiment weren't chasing headlines. They were trying to answer one of the oldest and most dangerous questions in all of physics, a question so fundamental that its answer threatens to rewrite everything we think we understand about time, information, and the nature of the universe. They sent the signal in, they reversed the system, they waited, and then something came back. What returned wasn't exactly what they expected. And for a brief, disquieting moment, the researchers in that laboratory stared at their data readouts and went very, very quiet. This is the story of the quantum echoes experiment, what it found, what it implies, and why some of the smartest people alive are still trying to decide whether the result should disturb them or whether it should terrify them. To understand what happened, you need to understand something that physics has been quietly wrestling with for nearly a century, something most textbooks gloss over, something professors mention once and move past quickly. It concerns a question you've probably never been asked before, but will almost certainly never stop thinking about once you have. Where does information go? Not data, not files, not memory. Information in the deepest, most absolute sense. The information that describes the precise quantum state of every particle in your body, every photon that has ever touched your skin, every atom that has ever been part of you. Physics tells us this information cannot be destroyed. This isn't a philosophical position. It's a mathematical law embedded in the foundations of quantum mechanics called unitarity. The universe, according to quantum theory, never forgets. It scrambles, hides, encodes, but it never, ever destroys. So when something falls into a black hole and disappears, where does the information go? Stephen Hawking spent decades wrestling with this and concluded, uncomfortably, that it might simply be lost. Gone. Erased. Which would mean physics as we know it is broken at its most fundamental level. This became known as the black hole information paradox, and it remains one of the deepest unsolved problems in science. It turns out that attempting to answer that question in a laboratory, not with a black hole but with a quantum processor, led directly to the experiment that stopped scientists cold. For decades, theoretical physicists had proposed a mental model. Imagine you have a book. You throw the book into a fire. The book is gone. But if you could collect every single photon and ash particle and gas molecule that escaped during the burning, and if you ran the laws of physics backward, you could, in theory, reconstruct the book. The information was never destroyed. It was scrambled and coded into the universe's most chaotic configurations, hidden in correlations between billions of particles, but it was never gone. This is the process physicists call quantum information scrambling. And measuring it, really measuring it, seeing it happen and watching it reverse, was considered essentially impossible. Until very recently, the reason it seemed impossible is buried in the strangeness of quantum mechanics itself. Once quantum information scrambles, it doesn't sit in one particle waiting to be read. It spreads across an entire system simultaneously, woven into the relationships between particles rather than into the particles themselves. To retrieve it, you'd have to reverse the entire system's evolution. You'd have to, in essence, run time backward. That is precisely what researchers at Google Quantum AI attempted to do. The machine at the center of this story is called Willow. It is a superconducting quantum processor containing 105 qubits, the quantum equivalent of classical computing bits, but operating under rules that defy ordinary logic. A qubit can exist in multiple states simultaneously. It can be entangled with other qubits, so that measuring one instantly affects the state of another, regardless of distance. And crucially, a quantum processor running at temperatures near absolute zero can perform calculations in seconds that would take the most powerful supercomputer in the world longer than the age of the universe to complete. That last claim is not exaggeration. It is documented fact. In 2024, Google's Willow chip performed a benchmark calculation in under 5 minutes. The same calculation would take the world's fastest supercomputer, a machine called Frontier, 10 septillion years. That's a 10 followed by 24 zeros. The universe itself is only 14 billion years old. So when researchers decided to use Willow for the quantum echoes experiment, they were working with a machine that operates in a realm of computational power that our ordinary intuition cannot begin to map. Here's what they did, and here's where things start to become deeply strange. The experiment works like this. Researchers prepare the quantum processor in a precisely defined initial state. Then they give the system a tiny, deliberate nudge, a perturbation so small it seems almost meaningless. They let the system evolve forward in time, allowing the quantum information to scramble, spreading out across all 105 qubits in a web of entanglement. Then they do something extraordinary. They run the entire evolution in reverse, like rewinding a recording. like pressing an undo button on the universe. The question they're asking is this: when you reverse the system, does the information come back? Does the echo return? To measure this, they use a tool called an out-of-time order correlator, an OTOC. The name alone should give you pause, out-of-time order. It measures something that shouldn't technically exist in a normal description of physics, correlations between a system's past and its future that bypass the ordinary sequence of cause and effect. The OTOC, as Google's lead quantum researcher Hartmut-Neven has described it, tells you how quickly information travels in a highly entangled system. It is essentially a probe of the universe's own memory. When the Willow processor ran this experiment, it ran it 13,000 times faster than the best classical algorithm running on the world's top supercomputers. The echo came back, measurable, unmistakable, verifiable. And then researchers looked more closely at what exactly returned. And that's when the questions began multiplying faster than anyone expected. But the echo itself wasn't the strangest part. In 2025, a separate team of physicists studying quantum scrambling in a different system, an atomic lattice configured in a pattern physicists call a nail state, made an observation that quietly sent ripples through the theoretical physics community. When they measured the OTOC in their system, they expected to see it decay smoothly and rapidly. That's what quantum information scrambling looks like. Information disperses, entropy wins, the echo fades. Instead, the OTOC decayed slowly, and it oscillated. It had a rhythm. The quantum information did not simply disperse into the chaos of the system and vanish. Instead, researchers found, according to their published analysis, that the information appeared to return periodically, as if the system partially remembered its past. Read that again. As if the system partially remembered its past. This was not a glitch. It was not noise. It had been predicted theoretically, but nobody had observed it experimentally before. They named it anomalous quantum scrambling, and it represents a new regime of quantum behavior that our existing models do not fully explain. Information that should have been irreversibly scrambled was, under specific conditions, reassembling itself, flowing backward against the current of entropy. Remembering, the implications of this begin to spiral outward very quickly once you start following them. Standard physics tells us that the universe has a direction, a flow. The past is fixed, and the future is open, and information, like water, flows downhill from order to disorder. This is why your coffee gets cold but never spontaneously heats back up. The name alone should give you pause, out-of-time order. It measures something that shouldn't technically exist in a normal description of physics, correlations between a system's past and its future that bypass the ordinary sequence of cause and effect. The OTOC, as Google's lead quantum researcher Hartmut-Neven has described it, tells you how quickly information travels in a highly entangled system. It is essentially a probe of the universe's own memory. When the Willow processor ran this experiment, it ran it 13,000 times faster than the best classical algorithm running on the world's top supercomputers. The echo came back, measurable, unmistakable, verifiable. And then researchers looked more closely at what exactly returned. And that's when the questions began multiplying faster than anyone expected. But the echo itself wasn't the strangest part. In 2025, a separate team of physicists studying quantum scrambling in a different system, an atomic lattice configured in a pattern physicists call a nail state, made an observation that quietly sent ripples through the theoretical physics community. When they measured the OTOC in their system, they expected to see it decay smoothly and rapidly. That's what quantum information scrambling looks like. Information disperses, entropy wins, the echo fades. Instead, the OTOC decayed slowly, and it oscillated. It had a rhythm. The quantum information did not simply disperse into the chaos of the system and vanish. Instead, researchers found, according to their published analysis, that the information appeared to return periodically, as if the system partially remembered its past. Read that again. As if the system partially remembered its past. This was not a glitch. It was not noise. It had been predicted theoretically, but nobody had observed it experimentally before. They named it anomalous quantum scrambling, and it represents a new regime of quantum behavior that our existing models do not fully explain. Information that should have been irreversibly scrambled was, under specific conditions, reassembling itself, flowing backward against the current of entropy. Remembering, the implications of this begin to spiral outward very quickly once you start following them. Standard physics tells us that the universe has a direction, a flow. The past is fixed, and the future is open, and information, like water, flows downhill from order to disorder. This is why your coffee gets cold but never spontaneously heats back up. And this is where the experiment begins to brush against territory that has barely been mapped. Here's where the story becomes impossible to ignore. The connection between quantum scrambling, time reversal, and black holes is not metaphorical. It is mathematical, precise. documented in peer-reviewed physics journals from institutions including Harvard, Stanford, Caltech, and the Institute for Advanced Study at Princeton. The black hole, in modern theoretical physics, is the ultimate scrambler. Information falls in. It gets distributed across the black hole's entire surface, encoded according to the holographic principle across the two-dimensional boundary of a three-dimensional void, and it slowly leaks out again as Hawking radiation. In principle, in theory, if information is not destroyed, then a patient enough observer, equipped with an instrument sensitive enough, could read the entire history of everything that ever fell into a black hole from the patterns in that radiation. The OTOC, the exact same tool used in the quantum echoes experiment, is the mathematical instrument physicists believe could theoretically detect this. It has already been used in thought experiments to describe how information would be recoverable from a black hole if the scrambling process is unitary. If information is preserved. When Google's Willow processor ran the quantum echoes algorithm and retrieved an unmistakable echo from a maximally scrambled quantum state, they were, in a very real sense, simulating what information recovery from a black hole would look like. They were running the Hayden-Preskill thought experiment, one of the most consequential ideas in theoretical physics, on actual hardware for the first time in history. And the echo came back clearly. The information was there. Researchers weren't prepared for the next layer of strangeness, because the quantum echoes experiment didn't just confirm that information can be recovered. It revealed something about how information behaves in quantum systems that sits awkwardly with several foundational assumptions in physics. The structure of what returned, the correlations, the interference patterns, the precise way the echo resolved itself, contained signatures that theorists are still working to explain. In particular, the experiment exposed what physicists call method-dependent behavior in the OTOC measurements. Different ways of measuring the same quantum correlations were returning subtly different results. Not because of measurement error, because the act of measuring itself, the specific protocol used to probe the system, was affecting what was observed in ways that weren't fully predicted. This is not a flaw in the experiment. It is a feature of quantum mechanics that cuts to the heart of its most disturbing philosophical implication. The universe does not have a definite observer-independent state until it is measured. Reality, at the quantum level, is not a fixed thing waiting to be discovered. It is partly constituted by the act of observation itself. When you send a signal into a maximally entangled quantum system and ask what comes back, the answer depends not just on the system, it depends on how you ask. Now consider what that means applied to the largest possible scale. The universe itself, according to quantum cosmology, began in a state of maximum quantum coherence. A pure quantum state, perfectly ordered, full of information. As it expanded and evolved, that information scrambled across an ever-growing number of particles and fields. The universe became its own echo experiment, running forward in time. Everything you see, every galaxy, every star, every stone, is the scrambled output of an initial state that has been running its own OTOC for 8 billion years. What the quantum echoes experiment asks, in its most philosophical form, is this. Could you reverse it? Could you, in principle, run the universe backward and recover the original state? Could the information of everything that has ever existed be retrieved? Physics says yes, in principle. The laws are reversible. The information is there. But here's the question that doesn't have an answer yet, the one that certain researchers in quantum foundation circles are beginning to ask in hushed tones. If the information is always preserved, if the echo always returns, then what exactly is the relationship between the forward direction of time and the past it encodes? Is the past truly fixed? Or is it, in some sense, always present, hidden in the scrambled quantum correlations of the present moment, waiting to be read? The anomalous scrambling result adds another dimension of discomfort to this picture. Recall that experiment, the atomic Neal state lattice, where the quantum information didn't just scatter and die, but oscillated, returning periodically, behaving as though the system had memory. This behavior had been theoretically predicted by physicists studying what's called many-body localization, a phenomenon in which quantum systems fail to thermalize, fail to forget their initial conditions, because interference effects prevent information from spreading completely. Normal materials forget their history. Heat them up, wait, and they settle into a featureless thermal state that carries no trace of what they started as. Many-body localized systems don't. They resist thermalization. They hold their memories. And the anomalous scrambling discovery suggests that the boundary between systems that forget and systems that remember may be more complex, more subtle, and more fundamental than anyone had realized. If quantum systems can resist forgetting, if information scrambling is not the one-way street it was assumed to be, then our picture of how the universe tends toward disorder may be systematically incomplete. Thermodynamics, entropy, the heat death of the universe, all of these rest on the assumption that information, once scrambled, is gone for all practical purposes. If that assumption has exceptions, and the experiment suggests it does, then the implications cascade through cosmology, through quantum gravity, through our understanding of time itself. Something even more unexpected happened when researchers began scaling the experiments. The measurement protocols used to probe quantum scrambling, the rewinding time method, the weak measurement method, the newly demonstrated irreversibility susceptibility method, each produced results that didn't perfectly agree with one another. Physicists working with trapped ion quantum computers discovered that each measurement approach revealed different aspects of the OTOC, different facets of the scrambling dynamic, in ways that were not fully reducible to each other. The scrambling itself seemed to mean different things depending on what you were looking for. Not because the physics was ambiguous, but because the OTOC, it turns out, is not a single clean number. It is a lens, and different lenses show different aspects of the same hidden architecture. This has started a debate in the theoretical community that may take a decade to resolve. What precisely is quantum information scrambling measuring? Is it one phenomenon with multiple faces? Or is there a deeper structure underneath? Some more fundamental object of which the OTOC is only an approximation that has not yet been formalized? Several teams at institutions, including MIT and Caltech, have begun publishing theoretical frameworks attempting to answer this. None of them fully agree with each other yet. What this means for the quantum echoes experiment is striking. The echo that came back from Google's Willow processor, clean, measurable, 13,000 times faster than any classical computer could verify, may itself be a partial picture, a silhouette of something larger, a shadow on the wall of a deeper cave. Let's step back and consider what all of this assembled together actually tells us. We have a quantum processor that can reverse the scrambling of information across a 105-qubit system and retrieve a clear, verifiable echo, simulating in miniature the information recovery problem from a black hole. We have a separate experiment showing that certain quantum systems don't fully scramble at all, that they retain memory, oscillate, resist the pull toward forgetting. We have a theoretical apparatus that connects all of this to the deepest unresolved paradox in physics, the question of whether information survives the most extreme environment in the universe. And we have measurement tools that reveal the phenomenon looks different depending on how you observe it. And somewhere underneath all of this, there is a question that none of the papers quite articulate directly, but that every researcher in this field is privately thinking about. If the quantum universe preserves all information, if nothing is ever truly forgotten, then what happens to conscious observation? What happens to experience? What happens to the information encoded in the quantum states of a mind, of a life, of a moment that ends? Physics says it is preserved, scrambled, encoded in correlations that spread to the boundary of whatever system contained it, but present. In principle, retrievable, always. That is either the most comforting thing you have ever heard, or the most disturbing. The experiment was named Quantum Echoes. The name was chosen for a specific technical reason. The echo is the return of a quantum signal after time reversal, but the word carries weight that its inventors may not have fully intended. An echo is not the original sound. It is what the environment gives back after the original sound is scattered through it, reflected from its boundaries and return changed. In a valley, an echo carries the shape of your voice, filtered through distance and terrain. In a quantum processor, the echo carries the shape of the original information, filtered through entanglement and chaos and the deep structure of time. What came back from Google's Willow processor, when the researchers ran the evolution forward and then reversed it, what came back was recognizable, measurable. It was the past, partially recovered from the present. Information that had scattered to the edges of a 105-qubit universe, recalled. The researchers who ran this experiment are careful, rigorous scientists. They are not given to dramatic interpretations. In their published papers, they write about quantum advantage and molecular simulation and the path toward practical applications in chemistry and material science. All of that is real. All of that matters. But the experiment they ran also demonstrated something that no human being had ever demonstrated before in a controlled, verifiable laboratory setting, that quantum information, scrambled beyond all hope of classical recovery, can be retrieved, that the past leaves echoes, that those echoes can be heard. One more layer. One final piece of evidence that the researchers themselves have noted without fully resolving. When the Willow processor ran the quantum echoes algorithm, the results were not just fast. They were verifiable by other quantum devices. This is crucial. It means the echo wasn't an artifact of this specific hardware. Other quantum systems running the same protocol found the same echo. The information encoded in the initial state returned, recognizably, across different physical implementations of the same quantum computation. This verifiability is what distinguishes this experiment from every prior demonstration of quantum advantage. Previous experiments could only be checked approximately, or required trusting the quantum processor's own output. This one could be cross-referenced. The echo was real enough to survive independent verification. What that means, in the most stripped-down possible terms, is this. Quantum information scrambling is reversible. Not metaphorically, not in principle only, experimentally, on hardware. The universe does not forget, and we now have a machine that can make it remember, at least in miniature, at least within the protected environment of a cryogenic quantum processor. The next question, which nobody has answered yet, is how far that principle extends. How large can the system be? How complex can the initial state be? Is there a size beyond which the echo becomes too faint to hear? Or does the principle scale without limit? Does it apply, in some sense, to every quantum system in the universe, no matter how large? If it scales, then the universe itself is an echo chamber. Everything that has ever happened is still present, encoded in the correlations between particles separated by billions of light years, waiting for a device powerful enough to reconstruct it. If that is true, then time is not what we think it is. The past is not gone. It is hidden. And we have just built the first instrument capable of beginning to hear it. There's a word in physics for a quantity that is preserved no matter what happens to a system, no matter how chaotic its evolution, no matter how thoroughly its information is scrambled across the maximum number of degrees of freedom the universe allows. The word is conserved. Charge is conserved. Energy is conserved. Momentum is conserved. And according to the foundational equations of quantum mechanics, information is conserved. It cannot be created. It cannot be destroyed. It can only be transformed. Scattered. Hidden. Encoded in configurations so complex that retrieving it seems beyond any practical reach. But seems is doing a lot of work in that sentence. Because the quantum echoes experiment has shown us that practical reach is not a fixed boundary. It is a frontier. And every frontier in the history of science has eventually moved. The researchers who ran this experiment were not trying to hear the past. They were not trying to retrieve lost information from the universe's own memory. They were trying to demonstrate a quantum computational advantage that had never been demonstrated before. They succeeded. The result was clean. The result was fast. The result was verifiable. But the implications of that result are still unfolding. In papers being written right now at Stanford and MIT and Caltech, in conversations happening at quantum computing conferences, in the quiet calculations of theorists who spend their lives listening for what physics is trying to tell us beneath the noise. The signal was sent. The system was reversed. The echo returned. What came back was information we didn't know we could recover. And somewhere in that recovery is a question about the nature of time and memory and the persistence of everything that has ever existed, that science has only just begun to seriously ask. We sent a signal into the quantum dark, and the quantum dark sent something back. Whatever it is, we are only beginning to learn how to read it.